Hello everyone, welcome back to the series How to in my class CSC 120. Today's topics are Subtractor and Multiplier. In this video, I'm going to show you how to design adder and subtractor circuit, how to design multiplier circuit, and discuss the simplifications that are allowed in a simulator like logism evolution. Let's get started with the 4-bit adder and subtractor circuit. Do you remember the 4-bit adder that I built in C3 video? I just loaded C3 video into Logism and expand the 4-bit adder to have this 4-bit adder and subtractor circuit. This one is a control circuit, which means that based on the value of the control input, it would be as an adder or a subtractor. If the control input is 0, then it's just a 4-bit adder. It will use the sum of the two inputs, A and B. So Q would be equal to A plus B. Otherwise, if the control input is 1, then Q would be equal to A minus B. Let me explain how I designed the circuit. The XOR gate here is being used as a control inverter based on the value of the control input. If the control input is 0, then the XOR gate will produce the output exactly the same with the input B. So I'll have A go to this input and B go to this input. So the 4-bit adder would add two numbers together and we'll have the final output is the sum of the two inputs. But if the control input is 1, then the XOR gate will invert the number B. So B0 will go to the 4-bit adder. At that time, control is also 1, so Cin would be also 1. We'll have the 4-bit adder will add A, B0, and 1 together. But B0 and 1, B0 plus 1, is actually the second complement of B. So we'll have A plus negative B. It actually, the A minus B is the output Q. So that is how the subtractor works. The control input here is just a 1-bit value. So I have to use a bit extender to extend the control input into a 4-bit signed binary number to connect it with the XOR gate. Since the XOR gate here, the data bit is set to 4. Thanks to Logism, this makes a lot easier to design the circuit. Otherwise, I will have to have 4 XOR gate. Each of them will have 1 data bit input. 3 of them will have to connect to the ground and the least significant bit of B will connect to one of the XOR gate, and the other input will be the control input. Then all 4 outputs of the 4 XOR gate will connect to the P input of the 4-bit adder. It will be a lot more complicated if I don't have the simplification that Logism allows me to use with the extender and the data bit input of the XOR gate. Alright, so that is the basic of the 4-bit adder and subtractor circuit. Let's test the circuits out. The input A, B, and output Q2, they are all 4-bit binary numbers with the radix set to sign decimal. But with sign decimal, you have to be careful that the range of the sign decimal is from negative A to positive 7. So you cannot enter input below negative A or larger than 7. I'm having A 6 and B is 5 and the control input is 0, so I'll add these two numbers together. So I would have the final output Q is 11, but if we do the 4-bit sign adder subtractor, then the Q2 is actually showing a wrong result because 11 is out of bound, since the output can show only from -8 to +7. So you have to make sure that the sum of these two numbers is below 8 and larger than -8. Let's test this control input, make it to 1. Then this circuit would be a subtractor, so 6 minus 5 will have 1 is the result. At this time, these two outputs, they're the same because they're all inbound and they're all valid. Let's try 10. I cannot enter 10, sorry. Let's say 7. No, let's say say 4. And change this one to 6, for example. So I'll do 4 minus 6. So you have -2 is the final output with the signed decimal. It's still inbound, but the unsigned decimal is something wrong actually. So you have to be very careful with the inputs and the output as well. So that's it. That is my 4-bit adder and subtractor circuits. So let's move on to the second one, the multiplier. After completing the adder and the subtractor circuit, it's time to go to the next operation, the multiplication. This one is the second circuit of today's video, the 4-bit unsigned multiplier. This circuit accepts two 4-bit unsigned binary numbers and produce the product of these two numbers as an 8-bit unsigned binary numbers. The circuit is very complicated, and I'll try to explain the circuit to my best by exploring this long multiplication operation right here. Right now I'm having A set to 10 and B set to 9. So the output is 10 times 9, which is 90. 10 times 9 can be rewritten at 1010 times 1001. For this operation, I will have to compute the partial products and add all these products together to have the final output. So for each partial product, I use the 4-bit 2-to-1 multiplexer to compute the partial product. As you can see that for each bit of the second numbers, if the bit is 1, then the partial product is the input A. Otherwise, if the bit is 0, like this blue bit, then the partial product is 0. So the two inputs of the multiplexer, one of them is connected to the ground and one of them connects to the input A. If the input of the select input of the multiplexer is 1, like this red bit, then the output of the multiplexer is the partial product is the input A. Otherwise, if the select input is 0, then the partial product is just 0, like the blue partial product here. So that's it. That is how I use the multiplexer to compute the partial product. The next step is compute the running sum of these partial products. You have to be aware that for each partial product from the second one, you have to shift them 1 bit to the left. I use the subtractor to shift these numbers, the partial product 1 to the left 1 bit, and 1 bit of the subtractor here is connected to the ground to fill in the blank. And the LSB bit of this partial product one goes straight to the output Q, right? This red bit 0 here goes straight down. The next thing to do is the 4-bit adder will compile the running sum of these two partial product 1 and 2. The carry out of this 4-bit adder will go to the MSB bit of the next 4-bit adder. The running sum 1 here will add with the next partial product 3, and then we'll have the running sum 2. The same thing goes for this subtractor right here. I shift this 1 bit to the left and add it with the partial product 4. So running sum 2 add with partial product 4, and I'll have the running sum 3. The running sum 3 will go to the output, and the CL will go to the MSB bit of the output. Right now the carry is 0, so I have 0 go to this output. So the output is 0 1 0 1 1 0 1 0, which is 90 in unsigned decimal. So that is how I designed this 4-bit unsigned multiplier. I hope that you can understand the operation and how I use the multiplexer and 4-bit adder to design the circuit. Thanks to Logisim hierarchical design, it allows me to simplify the circuit, because if you build a circuit in reality, it would be a lot more complicated. Do you remember the multiplexer that we built in the C5 video, the 4-bit 221 multiplexer? Would be even more complicated because this one is the 221 multiplexer. So the 4-bit unsigned multiplier circuit would be a lot more complicated in reality. So it's very nice that Logisim allowed me to simplify the circuit like this. I forgot to talk about this subtractor right here. I use the subtractors to shift the partial products to the left 1 bit. You can also use the shifter circuit, the one that I built in the last video, to shift the partial products to the left if you want. Alright, so that is how I designed the 4-bit unsigned multiplier. Let's test some input values. Let's change the input A to 14 times 9, so we have the product is 126. It looks correct. Let's say a simple one, 12 times 10, then we have 120. With the 4-bit unsigned binary input, the accepted range of input is from 0 to 15, or all 0 to all 1, which is 15. And with the 8-bit unsigned binary numbers, the output can represent up to 256 value from 2 to 255, right? So if I change this input B to 15, we have 15 times 15 is 225, is still a valid output. Please be aware that the input A and B, they are 4-bit unsigned binary numbers, so don't interpret them as signed binary numbers, otherwise it would be something different for this circuit. So let's say I change how I see the input A. A now is -1, and -1 times 15 should be -15, but the output is still 25. so that is not what we wanted. The 4-bit sine multiplier is a little bit different from this one. It's more complicated, and I'll save it in another video, so please be aware of the inputs and the output as well. Alright, so that's it for today's video. Thank you for watching, and have a good day.